Hey, what's up, guys? We're here for round two of ionic bonds. Yesterday's lesson focused on introduction to ionic bonds, what ions are, cations versus anions, what happens with the electrons in an ionic bond, how do we name ions. So we laid some groundwork that we're going to build on today. I've got my periodic table up here on the screen that I will refer back to, and also have a couple graphics that I will flip back and forth between. So if at any point you need to pause and back up and review, please do that. You've got the ability to do that. And also just jot down any questions or any comments or any feedback that you have for me as I do these video lessons. This is new to me, this is new to you, so hopefully it helps, but just give me some feedback. Tell me what works and what doesn't. All right, so we're going to jump into a second lesson today. We're going to talk about properties of ionic bonds. And before we get started, just a smidge overview. If you remember from yesterday's lesson, when we're talking about ionic compounds, let's get my marker going here. Ionic compounds are formed when we have a cation, which is a positive ion, joining with an anion. All right, so we've got something that is positive and something that is negative. Now, ionic compounds being formed between a cation and an anion, keep in mind that what type of elements tend to form cations? Well, those are metals. And that's because metals have valence electrons that they want to give away in order to get back to a full outer shell. Well, what type of elements want those electrons? Those would be nonmetals. Okay, so this is always the case here. Cations are formed with metals, and that's because they donate their electrons, or we can think of that as losing their electrons. We use those terms interchangeably. Whereas nonmetals, on the other hand, we say that they accept those electrons. And sometimes we say that they gain electrons. Okay? So this is fundamental here in understanding ionic compounds and being able to identify ionic compounds. Dead giveaway. If it is a metal and a nonmetal paired together, ding, 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 it's ionic compound, all right? So that's your first point of recognition in determining whether something is ionic or not, okay? Now, as we look at ionic bonds, remember these cations that are formed are positive, and these anions that are formed are negative. So an example of this, we have a sodium ion having given away one electron, has a positive charge. And let's say that that is pairing up with a chloride ion with a negative one charge. Okay, and that chloride ion has 7 valence electrons, remember, and it's taking on one additional electron. So because of that, it's got a negative one charge. All right, so when these two pair together, they form the compound sodium chloride. Okay, now, things that we want to recognize in ionic compounds. First off, the compounds are always neutral, meaning that the compounds, after they're formed, they never have a charge, unlike the ions that form them. So notice sodium chloride over here, no charge. And that's because the positive one and the negative one have kind of canceled each other out. So we have a one-to-one setup over here. One atom of, or one ion of sodium, I should say, has paired with one ion of chlorine. Okay. Now, what we see with ionic compounds is that positive to negative attraction creates some really unique properties. So that's a crucial point to understand. The positive to negative bond, and we call that an electrostatic attraction. If my handwriting is worse than usual, forgive me, because I'm trying to write straight up on the screen and it takes some getting used to. So the positive-negative bond, the electrostatic attraction in an ionic compound, creates some very unique properties. So that's what we're going to talk a little bit about today, those unique properties created. First off, we're going to look at the physical structure. How are these things put together physically? What do they look like? Well, ionic compounds, when the ions react together and they bond, they form solids, ionic solids, that are referred to as salts. Salts. Now, when we think of salt in the general sense of the word, we typically always think about table salt, sodium chloride. But in chemistry, the word salt is synonymous with any ionic solid. So that could be potassium chloride. That could be magnesium chloride. That could be lithium bromide. Any ionic compound that exists as a solid is referred to as salts, okay? Now, when we look at their physical structure, think about looking at a grain of salt under a microscope. What do you see? You see this kind of, we call it a grain of salt, but it's like this cubic form, right? And if we were to try to break that apart, all we would see is that it would just break down into smaller cubes. It would always keep that cubic structure there. We refer to that as, erase that. We refer to that as a crystal lattice structure. A crystal lattice. Now, that word lattice, if you've ever seen a lattice like at the bottom of a deck, it's this, you've got the wood slats that are kind of in that arrangement there. It's just this repeated pattern over and over again. That's what the lattice refers to. So this crystal lattice structure, as it pertains to ionic compound, it is we see the ions form themselves in a very packed, three-dimensional, repeating geometric pattern. And the reason it does that is because in doing that, we see that there's a balancing of the charges, those positive and negatives. Okay? So ionic compounds are solids. They are called salts, and they form this repeating crystal lattice structure. It's just, think of grain of salts, cube on cube on cube on cube, just to make a bunch of cubes. So a very repeated, rigid geometric arrangement now. Okay, so that's the structure. So now let's talk about the properties. How do these ionic compounds behave? Now keep in mind, all of these things, structures and properties, always will relate back to that fact that there's a very strong electrostatic attraction between the positive cation and the negative anion. Okay, so that dictates all of these properties and all of this, the physical structure. Okay, so the first property that we look at, because of this very, very strong attraction between the positive and negative ions, ionic compounds tend to have a very high melting point and boiling point. Very high melting and boiling point. Now keep in mind why. How does this relate to that strong electrostatic attraction? Well, what has to happen when things melt and when things boil, in terms of like the particles? we crank up the heat, and in order for a solid to go to a liquid, melting, those particles have to start moving around, right? And they have to get enough energy to where when they move around, they can flow past one another, and they can overcome that sticky factor, as I always refer to it. Okay? So it takes a great deal of energy for an ionic compound to overcome some of those attractive forces and start to move around within themselves, going from a solid to a liquid state. Okay, now think about how much more energy beyond that it takes for something to boil. When something boils, we have those particles that have enough energy that they can escape into the atmosphere. So they can overcome the attractive forces that's holding them down as a liquid, and they actually escape into the atmosphere. Now, ionic compounds don't want to do that. Have you ever melted salt, let alone boiled salt? No, you've not. It's possible, but you probably have never seen it, and I've never seen it, and it's nothing that we can create or recreate in our lab. So very high melting and boiling point because of that strong electrostatic attraction. So this is where I'm going to pull in a graphic it's in your textbook. This graphic here. Melting and boiling points of ionic compounds. So when we look at sodium chloride table salt, it's down here, okay? Look at that temperature, 801 degrees Celsius, just to get it to melt. Now, if we wanted to get it to boil, we got to jump up to 1413 degrees Celsius, all right? So very high melting and boiling points, even higher boiling points. Look at magnesium oxide, 2800 and 3600 respectively. So a huge amount of energy is required to get these things to melt, all right? Because of that very strong electrostatic attraction. They don't want to melt, they don't want to boil, they just want to stay bonded together. Okay, so now, next property. Solubility. Okay, solubility is the ability to dissolve. All right, now what happens when we put salt? Let's say when I say salt, I'm referring to table salt. So what happens if we put table salts, just good old sodium chloride, in water? We got a beaker of water, and we there's a grain of salt, and we throw it in the water. Of course, we've got salt water. We know, and the terminology we use is, we would say that salt dissolves. Okay, well, we have a new terminology now. What we encounter here is, stick with the same color. I'm just going to write this out in kind of a narrative, and we'll talk about it. In an ionic solid, or in an ionic compound rather, the compound, and here's a new word, let me back up. Yeah, we'll stick with that. The compound, new word, dissociates. Into its individual ions. All right, and when it does that, forming electrolytes, and those electrolytes can conduct electricity. All right, so if you need to refer back to that, or if you need to pause that to get that down, go ahead and do that. All right, so we've got our beaker of water there, and let's say this is our sodium chloride, and it goes into that beaker. And actually, I'm going to draw that beaker of water a little larger, just so we'll have some room to discuss here. Why not, right? We've got plenty of room. Okay, so in goes our grain of salt, and we've got sodium chloride. So here's what happens. When the solid, the ionic solid, and this is true for any ionic solid, when it goes into the water, what we find is that these two ions, now keep in mind, sodium chloride is made up of the ions, sodium with a positive 1 charge and chloride with a negative 1 charge. When we put it in water, the water creates an environment where those two ions that make up that compound, they kind of split apart. And it's like they're free to move about the cabin in airplane speak. So in water, those ions will dissociate from one another. Now think about what that word means, dissociate. If you associate with somebody or something, you come together. If you dissociate, you break apart. So these ions dissociate themselves in that water. Okay, so they're floating around as individual ions in there. And by definition, anytime we have ions that are in this aqueous solution, as we call it, we refer to those as electrolytes. Now you may have heard that term related to sports drinks and maybe dehydration. And the little biology link here is every muscle in your body runs on electricity. Okay, and those electrical impulses are created by the exchange of these electrolytes, because these things hold electrical charges. So every time a muscle contracts, there are some positives that are switched over and some negatives that are switched over. Okay, well, what happens if, as you're exerting yourself and you sweat, you lose all of these electrolytes? Have you ever been working out or playing ball and you get some sweat in your mouth that tastes salty? You're tasting those electrolytes: potassium, sodium, iron, magnesium. Okay, so if you're working hard and you're sweating out all of those electrolytes, and you've depleted your body of electrolytes, and you try to exert yourself and those electrolytes are not there anymore for your muscles to contract, you start cramping, because your muscles are saying, I need to contract, but I don't have the electrical requirements necessary to do that. So we drink some sports drinks. Actually, a common practice around these parts is to keep pickle juice on the sidelines, and you chug pickle juice because it's extremely salty, it's full of electrolytes, so that replenishes our body. So the point there being is that these things conduct electricity. So if you were to run an electric current through this beaker here with the salt water in there, you would see that you could conduct electricity through there. Current would flow. Now, what if we just had a big chunk of salt and try to pass an electric current through there? As a solid, not dissolved in water. As a solid, ionic compounds do not conduct electricity. They only conduct electricity if they are dissolved in water. Okay, so going back to this solubility, solubility is when they dissolve, and they dissolve in water. So now I'll add to this conductivity. Okay, and in terms of, well, by definition, conductivity is able to conduct an electric current. So specifically for ionic compounds, ionic solids do not conduct electricity. Because those positive and negatives, they're locked up as a solid. They're paired up with each other. Those electrons aren't free to move around. But when dissolved in water, ionic compounds do conduct electricity. And why? Because you've got those ions in there that have dissociated and they're allowing an electric current to flow through them. Okay. All right, I'm going to pause here for a second and then I'll shift gears. You won't see any difference. It'll just pick right up where I left off. All right, I'm back with you. So the next property we're going to talk about is the property of hardness. Hardness. All right, for ionic compounds, we find that they are very hard, for one, and they're also very brittle. And when I say brittle, I mean that they break instead of bending. Now we think about metals, and we'll talk about metals later, but metals will bend typically. That's one of their properties. They're malleable. That's not so with ionic compounds, and here's why. Let's go back to this image here. All right. So notice in this image, we've got this ionic solid here, this crystal lattice, and notice it's that repeated positive, negative, positive, negative. Okay. Now, in picture number 2 here, we've got a hammer that's hammering down on part of that solid, and it's applying a force on there. And just like with anything, when a force is applied, things are going to move. Okay, so when part of that ionic solid is moved, now look what happens. We've got this spot here where this positive lines up with this positive, this negative lines up with this negative, and that will just continue. Okay, now what do we know about like charges? If a positive gets next to a positive, they're going to repel. So when this solid gets hit by this hammer and those ions shift and they line up, positive, positive, negative, negative, there is this big repulsion that pushes them apart and it causes it to break. Think about if you hit a big chunk of salt with a hammer. It's not going to bend, it's going to break in a bunch of pieces. And if you keep hitting, it's going to break, into even smaller pieces. This is why. All right, so in terms of hardness, they're hard, but they're not bendable. They break instead of being able to flex, so they're not malleable. All right. So now let's get in, shift gears just a little bit, and let's talk about bond formation. And we'll drill it into the ground, the fact that when a cation, that's the positive ion, it gives up its electron to an anion. And remember that there is a full transfer of an electron or electrons. Full transfer. So in the case of sodium, and the case of chloride, remember this electron dot structure, these are valence electrons. So sodium as an atom has 1 valence electron. It doesn't like that, remember, because it wants to have 8. So it's going to give away that 1 valence electron. And in doing so, it will become positively charged by 1. Chlorine, on the other hand, really wants to have 8. So it's going to accept 1 electron, and in doing so, become positively charged. So there is a full transfer. So I made a positive sign there, should be a negative sign. So there's a full transfer of that electron. So now we've got a positive sodium, positive 1, and a negative chloride ion that come together and form the happy pair, sodium chloride. Okay, so now we see that relationship with any sort of cation and anion. So let's look at some other ones. And going back to the periodic table, remember everything that's in this first group here, the alkali metals, is going to have a positive 1 charge. Everything that's in group 2 is going to have a positive 2 charge because they're giving away 2 electrons. These are the weird guys. We'll talk about those later. Main group 13 or main group 3, excuse me, group 13, positive 3 charge. And then we get over into group 15, and this is where they start taking on electrons. So group 15 elements will take on 3, group 16 elements will take on 2, and group 7, or main group 7, group 17 will take on 1. Okay, so those are our charges. Now, when we look at the formation of other compounds, let's take, for example, lithium. It's in group 1, so it's got a positive 1 charge. Let's say that lithium was going to pair up with bromine. It's in group 7, it's got a negative 1 charge. And you'll start to remember these charges as you work with these. Now we're starting to develop this basic kind of chemical equation here, where we've got one ion plus another ion, or a cation plus another anion, gives us an ionic compound. So in the case of these two, lithium and bromine, look at the charges. So we got a positive 1 and a negative 1. So when these items react together, those charges essentially kind of cancel each other out. And remember, the compounds are always electrically neutral. So in this case, LiBr, positive, negative, it's lithium bromide. And that's another way that's how we name these compounds here. We say exactly what these ions are. Remember, we talked about those naming rules yesterday. So we say lithium, because that's the cation, and bromide, because that is the anion. And remember, anions end in an IDE. Okay, lithium bromide. Now, this is an example of what we refer to as a binary compound. And that binary word, bi, means 2. So literally what we mean here is that a binary compound has 2 elements. In this case, lithium and bromine. Okay? So now let's look at some more binary compounds. Let's say that we have magnesium with a positive 2 charge, because it's in main group 2. And let's say that magnesium is pairing with chlorine with a negative 1 charge. All right. So now, if we look at our charges, we've got a positive 2 and a negative 1. Now keep in mind that our compound, when it forms over here, is always electrically neutral. We have to have charges that kind of cancel each other out. Well, in this case, a positive 2 and a negative 1 do not cancel each other out, right? So what we encounter here is this scenario where it's going to take 2 of these negative 1 chloride ions to balance out that positive 2 charge of the magnesium. So when these react, we see this MgCl2. Okay? And this means that this is simply a 1-to-2 ratio. We have 1 atom of magnesium, and we took 2 of the negative chloride ions to balance out that positive 2 charge for the magnesium. Okay? So let's say we have lithium. Well, we've already used lithium. Let's use something else. Let's say potassium. Potassium is also group 1, so positive 1 charge. And let's say potassium is trying to pair up with oxygen with a negative 2 charge. Okay. Likewise, positive 1, negative 2. So they don't just balance out in a 1-to-1 relationship. So in this case, it's going to take 2 of the positive 1 potassium ions to balance out the negative 2 oxide ion. So K2O. And if we're naming these, this is going to be, we say the name of the cation, potassium. And then the anion will end in an IDE, oxide. Same thing up here, magnesium is your cation, chloride is your anion, IDE, IDE. Okay? Let's check this one out. So we have aluminum, and being in main group 3 aluminum has a positive 3 charge. And let's say that it's pairing up with oxygen, which will always have a 2 negative charge as an ion. Alright, this is not a 1-to-1, obviously. So let's take a look at what we have to do here. Alright, positive 3, negative 2. So I simply can't put an additional oxide ion here, because if I do that, now I'm working with, I've got a total negative charge of 4 negative. And I've still got a negative 3 or positive 3 charge over here. So that doesn't work. Well, what happens if I add another aluminum over here? Okay, so now I've got a overall charge of positive 6. So now I've got to have a negative 6 in order to balance out that positive 6. So if I had 3 oxide ions, now 2, 4, 6, I've got negative 6 in my oxides, positive 6 in my aluminums, and now that cancels out. So in this case, when aluminum and oxide react, it's going to take 2 atoms of aluminum and 3 atoms, or 3 ions rather, of oxide in order to reach an electrically neutral relationship. So this has to be a 2-to-3 ratio. Okay, and that could get a little time consuming, trying to figure out the lowest common multiple there and go from there. So I'm going to show you the super secret shortcut method. Don't tell anybody. Alright, so anytime, here's the rule. Anytime you have unlike charges, I'll write this down here. Anytime you have unlike charges, and when I say unlike charges, I mean unlike in number. They're always going to be unlike in charge, like positive versus negative. But when I have a 3 to a 2, or a 2 to a 3, or a 1 to a 2, so anytime they're unlike in the total number, anytime you have unlike charges, crisscross the charges and make them subscripts. Alright, so here's what I mean by that. Okay, see this positive 3 up here? That's for aluminum, and this negative 2, the charge for oxide. If you simply crisscross those, they become the subscripts for your final compound. That works all the time, 100% of the time. Every time. Okay, so now, these numbers down here again, these are called subscripts. They are the numbers at the bottom that tell the number of atoms. So this little 2 indicates that there are 2 aluminum atoms in that compound. The little 3, there are 3 oxide ions. And I should be more specific and say the number of ions, since we are dealing with ionic compounds. Okay, so just a few more examples of those. Let's say we have calcium with a positive 2 charge. And if you don't remember these charges right off, it takes some getting used to. You can look at your periodic table or your ion sheet. So let's say we have calcium with a positive 2 charge, and let's say calcium is trying to pair up with a nitrogen atom with a negative 3 charge. Alright, so when we look at those, we see, we've got a positive 2 and a negative 3. They're unlike charges in number, right? 2 and a 3. You can't do a 1-to-1 ratio here. So our rule says when we have unlike charges, we simply crisscross, and those charges then become the subscripts for the opposite ion. So the 2 came down here, The 3 came down here. So we have Ca3N2, and we would name that calcium nitride, an IDE, because it's the anion. Okay, so that's all I'm going to do today for this lesson. And for practice, I'll refer you back to the ion nomenclature packet that's in OneNote. And this page, on page 4, we're referring to, actually if we back up to page 3, this kind of reviews exactly what we just talked about, how these ions come together and we crisscross and we name them. So on page 4, this is your practice. So we have at the top sodium bromide. Keep in mind these are binary because these are, right now we're just working with 2 elements in the compounds. So sodium bromide. Here's how I would prefer that you do this as practice, because this will really help you get the hang of these. Take each name, each ion, sodium. Well, sodium as an ion is going to be Na plus positive 1. Okay. And that is being added to bromide. Well, bromide as an ion is Br with a negative 1 charge. Okay. So when those come together, we've got a positive 1 and a negative 1. They simply cancel each other out. And we end up with NaBr, sodium bromide. Okay. So I would recommend doing that for each of those. That way you can get in the practice of identifying the ions and their charges, and then canceling the charges out, crisscrossing if you need to, in order to get the compound. Now down here at the bottom, this is pretty straightforward. You're just naming, you're given the name in words of this compound. So you're just looking at the cation, in this case potassium, and the anion. In this case, there's oxygen, but as an anion, we name it with an IDE, oxide, potassium oxide. Okay. All right, so I'll stop the video there, let you practice. Hopefully, this got you going on your way, and the next video we'll pick back up with elements that have polyatomic ions in there, and then we'll progress to transition metals with multiple charges. Okay, if you have any questions, please email me and let me know. Give me some feedback on the videos. I would greatly appreciate that. And have a good day or night. See ya.